This video is going to be about astronomical distances. Because astrophysics uses quantities of distance much larger than those we see on Earth, measuring things in kilometers or meters is really inconvenient. So for astronomical distances, we use 3 units that you're going to learn in this video. The first unit is a light year, which we abbreviate lowercase l, lowercase y. A light year is the distance light travels in 1 year. 1 light year is the equivalent of 9.46 times 10 to the 15 meters. Another unit we're going to use in astrophysics is the astronomical unit, which will abbreviate uppercase A, uppercase U. An astronomical unit is the average distance from the Earth to the Sun. Okay? And to put this into perspective, how much less this is than a light year, this distance would take about 8 minutes for light to traverse. So it would be the equivalent of 8 light minutes. 1 astronomical unit is equal to 1.5 times 10 to the 11 meters. The largest unit we're going to use in astrophysics is the unit of stellar parallax, which is parsecs, which will abbreviate lowercase p, lowercase c. Let's start out by describing what I mean by parallax. So imagine that you're driving in this car. Far off in the distance, there's a mountain. And on the side of the road, there's a tree. So the mountain's far away, and the tree is close by. As we travel in the car from point A here to point B here, from position A, we see the mountain off in the distance, and the tree lies in front of us to the right of the mountain. And from position B, now that we've passed by the tree, the mountain's position really doesn't change, but now we see the tree behind us. We call this phenomenon parallax. And because of parallax, distant objects appear to stay stationary or not move, whereas the closer an object is, the more its position changes when you move. We can use parallax to find distances to a nearby star. For example, if this is the Sun, and this is the Earth orbiting the Sun, 6 months later, the Earth orbiting the Sun will be on the other side of the Sun. It's the roughly circular orbit of the Earth. We know that the distance from the Earth to the Sun is 1 astronomical unit. So the radius of this orbit would be 1 astronomical unit. I'm going to draw a line normal to the Sun and the orbit of the Earth. So if I have a very distant star in red, when you look up at that very distant star from the Earth, it should always appear in the same place. So when I look up at that star from the Earth the first time point, or if I look up at that star from the second time point, 6 months later, I still see that it's directly above me. However, this blue star, which is very nearby the Earth, will change positions due to parallax. So 6 months later, it'll appear to be on the other side of the red star, and we can use this angle, which we'll call angle P, to find this distance, d, to the blue star. We can do this by using the equation d is equal to 1 over the angle P. Now the angle P is going to be measured in a new unit of angle measurement that you haven't seen before. It needs to be measured in arc seconds, which is the equivalent of 1/3600th of a degree. And the distance in this equation is also in the new unit that I'm about to teach you. It needs to be in units of parsecs. Now, like I said before, a parsec is a very large unit of measurement. 1 parsec is the equivalent of 3.26 light years. It's important to make sure your equation is in these units in arc seconds and parsecs, otherwise this equation won't work correctly. While this is a really useful way to measure distances to stars and other astronomical objects, it has some limitations. It'll only work for a star up to 100 parsecs away from our solar system. This is because angles smaller than 0.01 arc seconds are difficult to measure from the surface of the Earth. Turbulence in the Earth's atmosphere causes stars to appear to twinkle, which makes small angular measurements impossible. Scientists have tried to put satellites outside our atmosphere so that they can make measurements using parallax without the atmospheric distortion. And so you can measure a little farther from a satellite in orbit than you can from the surface of the Earth. That's the end.